for having me here. I really appreciate it to have the possibility to conclude the first day and basically have the final word on anything I want. So I've been assigned the topic of non-thermal emission in supernovae, and so I'll really like to start from the kinetic energy profile of supernovae. And up until now, we have been basically considering the optical emission from supernovae. And we have been studying the optical emission from supernovae since a long time, and of course there is a reason. So supernovae are an optical phenomenon. By definition, we have something like 10 to 51 ergs in the optical emitting material, but only a little tiny portion of that energy is actually released in non-thermal emission. So the X-ray and radio emitting material is actually carried by, carries something like 10 to the 47 ergs in ordinary supernovae. And even if we consider the most extreme cousins of 1BC supernovae, those associated with gamma ray bursts, well, even in that case, we only have something like 10 to 50 ergs in the radio and X-rays. So this kind of make you stop and think about why should I care about something that is only carrying maybe 0.1% or even less of my energy. So I'll try to make this point in the next few slides. So we just heard a talk about Avishai about how by using the radiation from the explosion that happens in a few hours just after the explosion, we are really able to understand and map out the properties of the material that is very close by to my explosion. My argument here is that if we want to probe a material that is farther away, well, the only way we have right now is to use X-rays and radio emission. So basically what happens is that you allow your shock to evolve with time, you wait a little bit, and this shock encounters material in your environment that was left there by your star before exploding. This process accelerates particles, and that ultimately produces X-rays and radio emission. But there is a very nice property of that. Our shock is actually much faster. The supernova shock is much faster than the typical ejection velocity of material by the star before dying. That actually implies that every single time that we image something in the radio and X-rays at time t, well, that is actually probing a time scale which is 10 times, 500 times T back into the life of a massive star. So basically that is it really effectively acts as a time machine. So it's really, really powerful tool. Of course, if you want to learn about what happened before death, there are a number of different methods, and we already heard a lot about that today. But the point that I'd like to make here is that if we just forget for a moment about the galactic supernova remnants, well, the only way that we have to really learn directly about what a star was doing in the thousands of years, centuries, and thousands of years before explosion is really by using the shock, supernova shock, as a probe of the environment. So those are the three major areas that I like to define as major areas of ignorance in the field of supernovae. And in the remaining 20 minutes, I'll try to tell you something about our recent progress, especially in the understanding of mass loss in massive stars. So I'm going to concentrate on two particular results. The first is going to be about type 2b supernovae, and the second about the most stripped supernovae, so type 1BCs. I'm going to be using two supernovae, but I want to emphasize that I'm going to be using these particular guys just as tools, just to give you an idea about the general advances that we made. So we start with type 2b supernovae. We heard already a lot about those. Those are the cases where at the time of collapse, we still have some little hydrogen around the core. These are also a class of hydrogen-stripped core collapse supernovae for which we do know that, at least in a few cases, who are the progenitors. And they're usually luminous and massive stars, and usually yellow supergiants. So in a few cases, we knew about the progenitor before collapse. So we have the explosion. The explosion shock runs through this little layer of hydrogen. It heats up this material that later cools down. So this means that in the case of type 2b supernovae, we have in their light curve two different sources of emission. The first one is due to the cooling emission from the hydrogen envelope that was eaten up by your shock. And then at some point, this gets taken over by the nickel-powered emission, which is the standard thing we observe in type 1 BCs. So this is effectively what we expect to see in case of type 2b supernovae. So let's have a look at optical light curves of type 2b's. And we can clearly see that in a few cases, we actually observe this kind of thing. So a decay, and then we go back again to higher luminosities. Another example is 13DF with this double peak. 11FU is another case. However, it's also clear from these light curves that this is not always the case for type 2b classified supernovae. There are cases where this kind of double-peaked light curve is not observed. So I think that the best example is 08AX, but 11DH is another example where the cooling envelope emission was there, but it was not dominating the bolometric energy release. So it seems that the optical is already telling us that maybe the progenitor structure at the time of collapse for type 2b supernovae maybe is not always the same. So it might be that we actually are classifying as type 2b's things that are coming from stars with different progenitor structure. So let's have a look at the same guys, but now let's concentrate on the non-thermal emission. So let's have a look at these guys in the radio. We have been doing a pretty extensive campaign on type 2b's radio, and what you're looking at here is a compilation of light curves in the radio at different frequencies for this particular guy, but it is just an example. By monitoring the radio, this allows us to really quantify how much material the shock wave is encountering. So we can quantify the mass loss from my supernova from my progenitor before dying. And actually, we can put the type 2b supernova into this kind of plot. So on the y-axis, you have the radio luminosity, and the x-axis, you have the time of the peak in the radio multiplied by the peak frequency in the radio. Just concentrate right now on the red points, which are the type 2b's. So you can clearly see that they tend to sample a quite large range in the x-axis, while compared to the type 1 BCs, which are the blue dots, they tend to be much more clustered in their peak radial luminosity. So what is this thing telling us? So the velocity of the shock wave grows in this direction, while the amount of material that the shock wave is encountering with time grows in this other direction. So this thing is actually telling us that type 2b supernovae tend to happen in an environment with very different densities. So let's try to do this game right now. Let's try and see if we can connect the supernovae in this plot to their properties in the optical. So remember that I told that some type 2b's have a double peak light curve and some others do not. So if we actually plot the type 2b supernovae with a double peaked light curve in the optical, here is where they are. For 10p, we don't have the data, so I can tell. So let's now put on this plot the type 2b supernovae that did not show this double peaked light curve. And here is where they land. So it seems that what this plot is telling us is that every single time you observe a double peak supernova in the optical, which supposedly is telling you that the progenitor was very extended at the time of collapse, that is always related to a very thick environment around the star. While instead, when you don't have the cooling envelope emission, the star is exploding in a lower density environment. So this is another way of looking at the same thing, but plotting into two different variables. You have here, this is luminosity at peak times the time of the peak for the cooling envelope emission, and here is instead the time of the peak of the radio. So you can clearly see that every single time you have a prominent cooling envelope emission, the radial light curves tend to peak at later times. So what is this thing is telling us is that there seems to be a link between the progenitor structure at the time of collapse that is given away by the cooling envelope emission and the mass loss history, the very recent mass loss history of your progenitor star that is given away by our analysis in the radio. And the link that we identify is that the more pronounced is the cooling envelope emission, the thicker is the environment where you explode. And here is a way to put the type 2b mass loss that we inferred into the context of hydrogen strip supernovae. So what you can see here is that type 2b's are these blue dots, and you can clearly see that they tend to spread, that they are very spread over the density axis. And you can clearly see that there are some type 2b's that explode in environments that are very similar to type 1bc supernovae, but there are also type 2b's that really explode in very, very thick environments. Okay, so let's move on to the second topic. So now I told you something about supernovae that had some hydrogen at the time of the explosion, and then the hydrogen features went away, so type 2b's. Now I'm going to tell you something about the other way around, supernovae that were born without, and then they build up hydrogen. So I think that everybody was born with this idea that they are either type 1 or type 2 supernovae, and you can either belong to this family or this other. There are different colors, but you can cross it. And actually, what I'm going to tell you today is the case of a supernova, 14C, that was actually born as a type 1 supernova and then evolved into type 2. So this is a clear case when, if you ask two different people, what is this spectrum taken at early times and what is this spectrum, the same supernova at later times, they would tell you, oh, the first spectrum is a type 1b, the second spectrum is a type 2n. Okay? So let's have a look at 14C at early times. So let's have a look in the optical first. So I'll try to build up the picture with you. So I'll first speak about the optical, then the X-rays, and then the radio, and then they put everything together to understand what's going on. So at early times in the optical, 14C looked like a very, very standard type 1b supernovae. So either both in the volumetric properties and in spectroscopically. So the takeaway point from this slide is that it really looked like a normal supernova at the beginning. So what happens is that you wait a little bit of time, and with time the supernova started to build up hydrogen features, which is something we do not normally observe in a type 1b supernova. So there is a clear, very pronounced spectral evolution. So that's the optical. Let's have a look at 14C in the radio. Here you have luminosity versus time, and here is a bunch of type 1bc supernovae that have been observed in the radio. And let's put 14C on this plot. So you can clearly see that 14C shows a very late time bump in the radio. And the light curve stops here because we're still monitoring it. So suppose that instead you're an X-ray astronomer and you know nothing about what is going on in the radio and in the optical. So here is what happened in the X-rays. We do the same exercise that we just did in the radio, but we use X-ray versus time. So we did not detect 14C at 10 days, 15 days after the explosion, but 14C later developed a very prominent X-ray emission, which is something, again, that we really do not observe usually in type 1bc supernovae. And the reason is that if you explode in a wind density environment or in any environment where the density is going down like r to the minus 1 at least, the X-ray luminosity should also decline with time. So the fact that it's going up is telling you that something weird is going on for this supernova. The other very interesting thing is that not only we detected that in the X-rays, but it shows a very, very hard spectrum, which motivated our repointing of new star. And what you're looking at here is actually the first detection of extragalactic core collapse supernovae at hard X-rays. So this is an image of 14C. And actually, why is that so important? Because it's only by combining Chandra and Nuster that we could really constrain the temperature of emission so that we could really do some physics. So I would say that if he told me he would have been alive, that would be great for this kind of science. So what does that mean? Well, we could really constrain the parameters, so the temperature and absorption of as a shock wave was plowing through the material, which gave us the opportunity combining everything, which gave us the opportunity really to solve for the dynamics of the shock propagating into the environment. So let's put everything together, X-rays, radio, and optical. So here is the picture that we have. You can see that the H-alpha is growing, is building up. The X-rays are going up. Well, that's radio. The radio is going up. The X-rays are going up. And at later times, even the optical gets flatter. Why? Because it's getting some extra input there. So I think you already understood what is really going on here. So what's going on is that we had a supernova that started to expand into a hydrogen-poor medium. But for some reasons, at some point, it encountered a wall of hydrogen-rich material that caused a transition into a type 2N-like explosion. And we do know about the composition because we were doing a good job in the optical follow-up, because really optical and UV is what is giving away the chemical composition. So, and here is just a slide to say that only by putting together radio emission that is dominated by synchrotron, the X-rays, which are dominated by Bremsstrahlung, and the optical, we could really have a better handle on to understand what is going on. So I told you that this is a very fantastic data set. So what did we learn from that? So we could understand that the shock wave started interacting with a very thick material that is hydrogen-rich. It contains something like around 1 solar mass. It can be 0.2, can be 2 solar masses, depending on the geometry assumed. But the important thing is that something substantial. The other thing is that depending on the velocity of the ejection of this material, then it might have been ejected between 20 years and 2,000 years before stellar death. And here is where things start to get interesting. So we have to explain why, instead of having something like this is a very simplified thing, we have something like that. So what put there that wall of hydrogen? So what's the physics behind? And we have been hearing today a lot about binaries, and I believe that one of the possibilities is that instead of having a single massive star, we do have a binary companion. And binary evolution can actually help you out stripping your star by the hydrogen envelope. But that has to occur very late during the evolution. It must be something that happens almost synchronized with the explosion. It's not something that comes out naturally. The other possibility is that we have been maybe not giving enough importance to nuclear burning instabilities that might be there during the last thousand of years before explosion. That's something that Nathan already mentioned today. But the very important message here is that and maybe both things are there. Maybe both binary evolution and nuclear burning instabilities are actually tightly connected to what happens in terms of mass loss for massive stars before death. So not only winds, we really need to update our vision. However, if 14C, you can always tell me, well, 14C was a weirdo, so who cares? It's just one star. So in order to understand better the mechanism, I think that it's really important to have a handle of timescales, when that ejection might have happened, and how frequent is that? How many stars do have that kind of bump? And so I went back and used all the radio observations of type 1b supernovae that are public right now, and I looked for evidences for late time radio bumps. And this is just to remind you where the typical radio light curve of 1bc supernova peaks. And you can see that in 4 cases, I was able to find supernovae that peaked at later times. And PTF11QCJ is the guy that Brad Senko was discussing with us earlier today. And I could do this kind of job for 40 supernovae. That means that for this particular sample that is in no way free of biases, we could find evidences for interaction of the shock with a thick environment in 10% of cases. Why is that important? Because if you if Selma and Manos do binary population synthesis, well, it turns out that the fraction of progenitors of 1BCs that do go through the common envelope phase later enough in their evolution so that the ejection happens very close to the time of death is actually comparable. And I find these results encouraging. What we are doing right now is actually trying to compile a controlled sample of supernovae, to really understand how common is this and when that happens. And also, it would be extremely important not to have only radio, but to have radio, X-rays, and optical to really pin down the emission process. So in general, why should I care so much? Yeah, why should I care so much about this mass loss, about what happens in the last 1,000 years? Well, I think that this kind of thing might have a very strong impact on the structure of the progenitor, the atomic collapse. And today we already heard a lot about how important is that to determine if a star might explode or not. And even if you don't care about stellar explosions, I think that there are good reasons to still be interested. And always remember that mass loss from massive stars is the way that massive stars use to enrich, chemically enrich our universe. And this kind of process also has some impact on the understanding of star formation, the star formation history of the universe. So we clearly have, I told you that we clearly have this knowledge gap in terms of mass loss from massive stars. And I just told you about our recent progress that we made using X-rays and radio observations of supernovae. And sometimes I know that people complain because what is really happening is that our knowledge grew, but at the same time the ignorance also grew, which is that boundary there. But I believe that is exactly what we have to do. The more you know, the more questions you're gonna receive. However, and there is a advertisement time. So if we want, I believe that if we want to have this knowledge blob grow faster, it's really, really important for each of us to have access to data. So if you happen to publish a paper, please make sure that the data are really public. And now you can really do it very easily. And there is a website that James Gishan, Jen Parent, and myself are involved with. It's www.supernovae.space. So you have the platform to do that. And with this, I say thank you for your attention.
So the correlation between the wind density that you see and whether or not there is a cooling envelope in the type 2Bs is really interesting. Have you looked at or thought about this in these terms? So a more extended star has a larger radius and a lower escape velocity and a slower wind and a denser wind, even for the same mass loss rate. So is your difference in density easily explained even with the same mass loss rate, or do you need different?
That's a very good point. Yeah, I thought about that too. And actually, so the problem is that we can't really measure the wind velocity. So it's usually just an assumption in our. So what we really measure is m dot over v wind. This is what the radio and X-rays are really sensitive to. So if you put in the wind velocity and you can say, well, maybe the wind goes from, instead of being 1,000, it's 10, then yes, readjusting the wind velocity, you can make everything right again, yes.
Yeah, I mean, I guess you could ask how big the difference in the radius needs to be in order to explain it with the.
Yeah, I should check on that, yeah. But I know that if you can change the wind velocity of a factor of 100, yes, you can reconcile, mostly.
You know, we have a pretty good example of a case where there was a lot of mass loss and where there's now a high-density zone that is affecting both the X-rays and the radio, and that's 87A.
Yes.
So it might be interesting to put it on this same plot. You're at a time scale that's 30 years, which you have no other examples of, but just because it's possible for you to measure things out to, say, 1,000 days or a few thousand days, doesn't mean there aren't things where those phenomena take place on a longer time scale. And 87A might be an instructive example of, you know, how nature has imagined things that, you know, you haven't quite gotten to here.
Yeah, totally agree with you, yeah.
So maybe I missed it, but I don't think you talked at all about the iron K alpha line in the spectra, the X-ray spectra, 14C. Do you want to say something about where that's coming from?
Yeah, there's actually a reason why I didn't say anything. Anyway, so yeah, we do have emission that is likely associated with helium-like or hydrogen-like iron. Let's see if I get it. Sorry. And so here, the problem that we had with the interpretation of that feature is that it's not the presence of it's this thing. this little thing. I think that, yeah, so you can see that here. Here I just fit the thing with a single profile, but it's likely the blending of two, but it didn't have the resolution to see it. Anyway, so it's not a problem that it's there, because so here is the temperature is 20 kV, and and the only element that can possibly survive is iron, fine. But the problem is how strong is this line? And actually, with a 20 kV plasma, you should inhibit line emission, and you're not able, I wasn't able, to fit both the continuum and the strength of this iron line. So how do we solve that? So one possibility is that you require the metallicity to be 10 times solar, which is pretty extreme, I would say. Or the other possibility is instead, I think the other possibility, which I believe is more likely, is that the continuum is dominated by this 20 kV plasma, but the medium there is likely not homogeneous, so you have clumps. So the actual velocity of the shock within the clump is lower, which means that the actual temperature there is lower, and that might give you, for free, a more pronounced iron line.
I have a question about 2014C. At the early time, you're saying that there's no hydrogen feature, but the hydrogen shell exists already, right? You do see, I mean, you do see narrow hydrogen emission at late time. So what's the explanation that why you don't see the narrow emission at the beginning?
So there is a little tiny hydrogen, which is a contribution from the host, and likely something that is already there. The idea that I have in mind is that most of the hydrogen was actually farther away. So you see, there is a little guy.
Oh, you do see it beginning,
yeah,
that early time.
But most of the hydrogen, I think that it was just at the right location, this shell, so that it wasn't ionized at the time of the explosion, like at the beginning. But it was not. So it wasn't super close to me, but at the same time, it was not that far away that my monitoring would have just missed it. It's kind of in a sweet spot, but it's still there a little bit.
I have a comment and a question. The comment is that 11DH definitely did have two peaks.
Yeah, it's not.
So
yeah.
you just don't plot the early data from Margutti et al., but it's there.
No. It did have two peaks. When you put it together in the bolometric luminosity, it's not dominating.
How do you know the bolometric correction for the early peak? There's no color information.
There was, for 11DH, I think that you had UV from Swift UVT to the optical, so I think you can have a good idea about the bolometric luminosity.
I don't think, well, you cannot because it wasn't discovered at the time. Anyway, I don't think you have for the really early data. And the question is about this. This is really a fantastic data set, 14C. So at the late times, it interacts with this material, and you observe it with new star. So it's a little bit like a type 2N supernova. So did you look at comparison with the 2010 JL, which is this type 2N supernova that was also observed with Chandra and new star?
Yeah,
so
yeah.
does it have the same features that you see here?
Yeah, the statistics is a little bit poorer for 10 JL because it was farther away. It was 50 megaparsec. This one is just around the corner. But yes, we did compare, and that's amazing that the temperature of the shock is 20 kV in both cases, and temperature speaks to the velocity of the shock. And the other thing is that that really compares well is the presence of the iron-like emission that you also have in 10 JL. Yes.
I'm certainly not an expert on supernovae, but I would not call that as type 2 supernova. The velocity of the line matters. Just because you see hydrogen, which is essentially at rest and then broadened, obviously by shock interaction, that's sort of a bit loose, I would say, loose classification. So
No, I agree.
it's a type 1 that's interacting, that's all.
I totally agree. It was a provocative way of presenting a supernova, but it's also funny when you try to classify the spectra and you don't know that it's the spectra from the same supernova, then if you go through, if you ask to people or if you go through tools, they would put it in type 2N and type 1B, so.
Provoking Shri is not a good. Okay, one final question.
Thank you. Have radio surveys ever detected such an event serendipitously, or is it something to think about for the future?
Like 14C, you mean?
Yes.
Yeah, so actually, Actually, there is, I think that the analog of 14C, and of course I'm not finding it, the plot, but the analog of 14C is O1EM. So O1EM is a type 1C broad line that people thought it was actually connected to a gamma ray burst. And that showed a later time peak, a later time rebrightening in the radio and in the X-rays. In that case, it was a little bit serendipitous because people were not following it continuously from beginning to the end, but it was discovered it was followed up at the beginning for, let's say, 50 days, and then it was dropped, and then rediscovered that he rediscovered as an H-alpha emitter 2 years afterwards. So yes, there was serendipitous discovery, yeah. Thank you.